everyone. Myself Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering in Institute of Aeronautical Engineering, Hyderabad. So I'm going to deal with the course Computational Dynamics, and the topic which I'm going to deal is Introduction to Computational Fluid Dynamics. So we'll see basically how the computational aerodynamics will be useful in the different applications of engineering and medical applications. So then after we'll be going to the techniques that is being used in computational fluid dynamics. Okay, so basically here the course name is computational dynamics because so basically the term fluid, whatever we have here, so can be gone into like water or air. So since we are dealing with the aeronautical engineering, so since we are dealing with aerodynamics and the stuff, so the fluid what we are taking is air. So that's why we had considered here it as like aerodynamics. Okay, so this is what we have. So we'll see basically first why computational aerodynamics. So previously when computational aerodynamics have not evolved, so how the problems have been solved, we will be seeing here. So first, if you see here in this triangle, so you have the experimental technique and you have theoretical techniques, and here the third form is computational fluid dynamics. So before 17th and 18th centuries, so this computational fluid dynamics tool has not actually evolved or not emerged actually. So before that, so people used to solve any fluid flow problem or a heat transfer problem using experimental techniques or pure theoretical techniques. So let's say you have any, let's say, heat convection equation. So dou square x by dou square of T one dimensional is equal to some heat generation by thermal conductivity. So if you have this equation, so if you want to solve this equation, so people used to actually solve using analytical approach and get the temperature distribution along any like a rod or any plate or this kind of thing. So this will fall into pure theoretical technique. And when we are seeing the experimental technique, so people will have a laboratory setup, and so basically so here let's say you have a laboratory setup, so some setup here, and you will have a test section model, so where model will be mounted here. So the temperature, whatever the distribution that is being coming from the plate, will be observed using some readings or some other measuring units, and get the values across the plate or rod, this kind of thing. So this is coming to like pure experimental setup. Okay, but when we see these approaches, so when you have this experimental approach and theoretical approach, so we have some limitations. So it is a time taking process, or if you want to perform experiment or analytical process for a full scale model, let's say if you want to do flow analysis over a full scale rocket, or let's say a full scale aircraft or a full scale car, or these kind of things, it would cost you more actually. So coming to cost for a pure experimental setup for a large scale models, so here we have the pure experimental setup and pure theoretical setup, and we have pure computational setup. So when it is coming to pure experimental setup, so the cost will be more, and analytical approach, you will have so much time taking process by solving analytical approach. The third approach which we have is like computational fluid dynamics. So it will actually replace it will actually combine these two, so the experimental and the theoretical one. So it is a third approach actually, which is a beneficiary approach, which will reduce the time and the cost to solve a fluid flow problem and a heat transfer problem. Okay, so basically the computational fluid dynamics tool is used to solve the governing equations of fluid flow and heat transfer problem and give the solutions to the any fluid flow problem. So this is the third approach of CFD. Okay, so we'll be seeing what are the processes that are involved in the CFD. So first we need to select what is the fluid problem actually. So whether the fluid is an incompressible flow fluid or an compressible flow fluid, or whether the fluid is having any heat transfer phenomena, or whether the fluid is traveling Mach number greater than 1 or Mach number less than 1, or let's say if a fluid it is a water or a honey, or let's say, so any kind of fluid flow phenomena we can take. So first you need to see what is fluid problem, so which fluid problem we are solving. So then, so what is the mechanics behind it actually, so what are the governing equations so that we will involve, so those things also we need to be seen. But before that, so you need to see what is the problem that we are going to solve. So then once we decide what is the fluid problem, then what is the physics of the fluid. So in this, so basically we will be seeing what type of equations or what type of assumptions we can make, and what type of model we have to choose. So these things will be there. So then, so we will go into the Navier-Stokes equations or the partial differential equations which we have. So like, let's say if we have an incompressible flow, and so for the incompressible flow, so you have only three equations to be solved. Let's say if it is a 2D incompressible flow, so you have x momentum equation, and y momentum equation, and continuity equation. So total you have three equations, and you have variables such as u velocity, so v velocity, w velocity, and you have pressure. So if you give input as a pressure, so you will have variables u, w will be actually, it is neglected. So therefore u, v, and p. So you have three variables and you have three equations. So you can solve this equation. So this is how actually first you need to determine so which type of fluid flow problem that we are taking, and what type of governing equations we are taking. Okay, so once we actually first determine the set of equations, then we need to see what are the discretized form of equations. So here, let's say in the continuity equation, you have du by dx, dou u by dou x. So this dou u by dou x has to be replaced by a algebraic set of equation. So you have a continuity equation, let's say du by dx plus dv by dy is equal to 0. So this is like partial differential equation, and then after you have momentum equation, let's say du by dt plus u into du by dx plus v into du by dy, so is equal to minus 1 by rho dou p by dou x, let's say. So we have this equation. So here the equation 1 what you have, and equation 2 what do you have. So basically these are partial differential equations. So we need to replace these partial differential terms, dou u by dou x or dou u by dou y, dou p by dou x. So these terms as algebraic expressions. So this is nothing but a discretized form. Okay, so this is what we have in the discretized form. So once we divide the or once we form the discretized form, then we will see what type of grid we are choosing actually. So whether we are actually, this kind of discretized form is applied at the grid points. So we'll see in future slides what are the grid points, what is the mesh and everything. So once the discretized form and the grid and the boundary conditions, everything is done, so we'll be using the computer code and solve the results, and we'll get the post processing. So basically these are the process involved in a computational fluid dynamic approach. Okay, so basically these three are the major important governing equations which will determine or they govern the fluid flow phenomena, whether it is an internal flow or the external flow, okay, or a micro flow or any kind of thing, or heat transfer problem kind of thing. So you will be using these three equations. So the first equation is the continuity equation, and the second equation is the momentum equation, and the third equation is your energy equation. So basically continuity equation and the momentum equation, so these two equations are used for incompressible flow problems. So where the density is considerably constant, then after since the density is constant, you don't have any compressibility effect, so temperature or the energy equation will not come into picture. So therefore solving equation 1 and equation 2 will be sufficient to get the flow parameters of u velocity, v velocity, w velocity, and pressure. Okay, so this thing what we have. Okay, so if it is a 2D equation, then you will have only u and v, and so p, u, v and u. Okay, so this is what we have. So coming, like when we are solving a compressible flow equation or a heat transfer problem, so we need to take all the three equations into account. Okay, so you have to take continuity equation, you have to take momentum equation, and you have to take energy equation into account to solve a fluid flow problem or heat transfer problem. Okay, so if you take any flow properties, so basic things what we have is like, so you will have velocity, u velocity, v velocity, w velocity, pressure, density, temperature. So these are the basic properties of the fluid. So u velocity, v velocity, w velocity, pressure, density, and temperature. So these are the flow parameters. So depending upon the equations that we have, depending upon the flow that we have, so we will neglect some parameters. But if you have all the things, let's say the flow is compressible and you don't have any temperature effects to be negligible, then you have all 6 parameters, which say u velocity, v velocity, w velocity, pressure, density, and temperature. So all the parameters has to be solved. So but here the problem is, so you have 6 variables, but you have only 5 equations. Let's say, so this first equation, continuity equation, what we have is a scalar equation. Okay, so the continuity equation whatever we have is a scalar form actually. But here if you take this momentum equation, it's a vector form. So here the momentum equation, what it is coming is from, is like mass into acceleration is equal to force. So on the left hand side, whatever terms we have is about the acceleration of fluid particle. So it's like dou u by dou t, or del dot rho u u u. So basically these terms will contribute to the acceleration of fluid particle. On the right hand side, whatever the terms we have, so the first term is the pressure force, and the second term is the shear force, and the third term is the body force term. So depending upon the flow phenomena that we have, so we will use these kind of forces. Okay, so here you have a pressure force term. So basically the flow will go from one region to other region with the phenomena of pressure difference, which is nothing but dou p. Then after, like here you have the shear force term. So any fluid particle you take, like fluid, if it is passing over the car or let's say bike, so you'll have pressure force and shear force acting on those bodies. And the gravity, like the body force, depending upon the flow phenomena that we have, we will take gravity force. For example, if you have a vertical flat plate, heated flat plate, so you have a flow which is going vertically, so the gravity force will act on fluid particle, which will pull it down vertically downwards. So here you need to use the body force term, which is rho g. So this is very important. So then after, like we will be having energy equation. So where here the conservation of energy, whatever the equation we have, we will be using. So H is nothing but enthalpy, which is CPT. So basically in the energy equation, we'll be solving this equation to get the value of temperature, and we will be considering some assumptions where, let's say, radiation is constant or radiation is negligible. Okay, if there is no heat diffusion, if you take these things, the equation will get simpler. So the problem is like you have more number of fluid parameters. Let's say you have 6 fluid parameters, and you have, let's say, 5 equations. So in order to solve fluid flow parameters or any linear or algebraic equations, the number of variables and the number of equations must be equal actually. So therefore that is consistent, and it gives a solution. But here what we have is like, here we have only 5 equations, let's say in scalar form. In the vector form, whatever we see, we have only 3 equations. Okay, in the vector form you have three equations here. So this whatever equations 1 and 2, 3 you are seeing here. So these are the vector form equations. So in the case of vector form, you have u, p, and t and rho. So let's say you have three equations and four variables. So here also you have one extra variable. So you require one more equation. And we can consider an equation which is ideal gas equation. So which is p is equal to rho RT. So there you can get actually additional equation to solve this kind of problem. But the main important thing is that first you need to know, so what is your problem, fluid flow problem, then what are the assumptions need to be taken. Okay, so after the assumptions, how the equations are reduced. Okay, so let's say, so here we can make some assumptions, and I will remove some parameters, so where the equation will get simplified. So let's say if the flow is said to be incompressible and steady. So in the case of steady, what happens? So this parameter, and this parameter will be neglected. Okay, if it is incompressible, so this equation would be reduced to del dot u is equal to 0, so which is of simplified form, and this density parameter will come out and it will get divided by rho. Okay, if you take shear force negligible, so this parameter will get cancelled, and if you take body force negligible, this parameter will get cancelled. So you have this simplified form of equation here. Okay, so if you take this parameter and the radiation parameters are negligible, so then after you have the simplified parameters. So the full form of, instead of solving full form of equations, we take some assumptions and we actually go for an approximate solution. So basically CFD approach, the numerical approach, whatever we are doing, so we'll go to the approximate solution, not to the exact solution of a fluid flow problem. So let's say if the exact solution is, let's say 4.5 meter per second, so CFD may give like 4.4, 4.49 or 4.4856, something like that. Okay, so it will be going to the close to the exact solution. Okay, so here basically you have different types of flow. So you have external flow, and so first type of flow is like external flow, and here the example what you are seeing is like the wind turbine which is rotating. Okay, so with certain angular velocity, so the flow will be going, let's say, from the left to right. Okay, so when the flow is going with uniform velocity on the wind turbine, so it will add some air loads on the wind turbine. So how the flow is deflected and how is the wind turbine is deflected with the presence of fluid flow, we will be seeing. Okay, so this kind of an example is nothing but it is an external flow. So you have an other flow is called internal flow. So here you can see basically here let's say an example called like a mixer grinder. So here you can see these blades are rotating with certain angular velocity. So whatever the mixture that is present inside this grinder, so these particles will be rotating with certain angular velocity, and this concentration of the particles and velocity contours we can see in this the CFD approach. So this is an example for internal fluid flow. So coming to so here you have an external flow parameter example, and you have internal flow parameter example, and let's say what type of approach will be going in the CFD we'll be seeing. So here you can see there are actually two types of approach for fluid flow problem. So one is called the Eulerian approach, other one is called the Lagrangian approach. Okay, so basically if you take, so this whatever the diagram that you are seeing, so flow through a channel. So here the dotted particles what you are seeing is like these are the fluid particles, let's say. Okay, so let us assume these are the fluid particles. Okay, so these fluid particles will be having certain velocity at different points at different cross sections. Okay, so basically this is one cross section, this is one set of cross section, and this is one set of cross section. So at different cross sections you have different velocities of the fluid points. Okay, so here if you see, okay, a fluid particle which is coming, it will have certain velocity. At this point it will have different velocity, and at this point you will have different velocity. So if you want to track a single fluid particle and get to know the properties of a single fluid particle throughout the time and space, okay, so basically the velocity of the fluid particle is function of x, y and z and time. So this is nothing but your space coordinate, and this is nothing but your time parameter. So if the velocity is function of x, y, z and time, so you need to actually get the velocity of this fluid particle about x, about y, about z, and with respect to time how it is changing. Okay, so in the Lagrangian approach, so if we are concentrating only on single, like individual amount of fluid particles, so let's say you have particle A here, particle B here, particle C and D. So in the Lagrangian approach, the velocity or the flow parameter will be given or will be calculated for a single fluid particle. It's like tracking a single fluid particle. So these type of approaches, Lagrangian approach is used only at higher altitudes of the Earth's surface. Let's say where the density is less, or you have only less number of fluid particles at higher altitudes of Earth's surface, and in the micro or the nano fluid regions actually. So where you have, so if the density is less, so you have less number of fluid particles. So at that region, so you can use this kind of Lagrangian approach. And you have another approach called Eulerian approach. In the Eulerian approach, so you will be calculating the flow properties of let's say pressure, temperature or velocity, density at a given cross section. It is nothing but an average quantity. So the difference between the Lagrangian and the Eulerian approach is like, so the Eulerian approach is used for the continuum flow. So where the fluid particles are continuous with respect to space and time, and you will get to know the fluid properties, so which are being taken average estimation. Okay, in the Lagrangian approach, you will be calculating or you will be estimating for a single fluid particle. So this is the difference between the Eulerian and the Lagrangian approach in the CFD. Okay. So here basically you will be seeing the grid. So there are two types of grid, actually structured and unstructured grid. So once we will be seeing the grid phenomena, then we will apply the boundary conditions and solve the fluid flow problem. But let's see what is this grid actually. So what is the importance in the CFD? So here whatever the entity that you are seeing, the outer entity, so the circumference, the outer entity, this enclosure is nothing but domain actually. So the entire thing whatever you are seeing is nothing but a domain. Okay, so for a given domain, so basically this is a rectangular domain. So the overall shape of this picture whatever you are seeing is a rectangular one. So and this domain will consider or will consist of subdomains. So here you can see you have subdomains. So you have small size particles of square or rectangular cells or the rectangular shape, okay, domains. So you have different domains actually. So base here if you have flow as an external flow, so basically we will perform this grid operation over the domain. So let's take an example of flow over flat plate actually. So let's consider this bottom surface whatever we have. So this bottom surface, so you have surface, like let's say this is inlet and this is outlet. So here you have inlet and this is flat plate wall and this is like far field. Okay, so you have like 4 edges on this bottom edge. So we will consider this as a wall which is flat plate, and here you will have inflow and here you have outflow, and here you have, it is called far field actually. Okay, so basically what we are doing here is, like let's say the example is for flow, external flow over of the CFD actually. here this is taken as a flat plate, and we are interested to see what is the flow parameters, like flow behavior over the flat plate, right from the starting, which is called leading edge, till ending, which is called trailing edge. So if you want to see the flow properties over a flat plate, then you need to perform mesh over the flat plate. Okay, so how it is all we'll be seeing. So you have some lines actually, so these are like x lines. Okay, so there are lines which is going along x direction, so there are lines which are going along y direction actually. So there are so many lines which are going along x direction and so many lines which are going along y direction. So the intersection of these two lines will give you a point called grid point. Okay, so the intersection of these two lines, so here you can see you have a grid point here, you have a grid point here, you have a grid point here, you have a grid point here. So basically intersection of x line and y lines will give rise to grid point. So the combination of these grid points, so if you join all these 4 grid points, you'll get a cell. Okay, or a what do you say, grid cell. Okay, so the combination of all 4 grid points. So this is called structured grid because so no two x lines will meet each other at any point and no two y lines will meet each other at any point. So that is why we call it as a structured grid. So here what we are doing is like, so we will apply the boundary conditions on these 4 edges. So this is nothing but the inflow. So let's say you are seeing 2 meter per second velocity inflow. Okay, so this wall is located at 288.15 Kelvin temperature. Okay, so this is outside, like this is 1 atmospheric pressure outside, and here also you have 1 atmosphere pressure. Okay, so these conditions we will apply for the domains, and we will see how the flow is behaving. Okay, so what is happening in this grid point is like, so at each and every point, so these whatever the continuity, momentum, energy equations are there, so we need to solve these equations. Okay, so we need to solve these governing equations at all these particular grid points and get the solutions of this domain. So to get u velocity, v velocity, w velocity, pressure. Okay, so if you want to get these flow parameters over this domain, so you need to solve the equations, governing equations at each and every grid point and get the flow parameters. Okay, so this is how we solve a CFD problem using appropriate numerical techniques. Okay, and we will see in detail about the types of grid in the next lecture. So here we are learned about structured grid, and we are learned something about the boundary condition, like let's say inflow, outflow, far field, and here we are seeing the wall boundary condition. Okay, so we'll see other things in the next class. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.